Good morning, everyone. We hope that you're well and that you enjoyed day one of the hackathon. We are thrilled to be beginning day two with this technical workshop. Before we begin, I'd like to do some housekeeping and an acknowledgement of country. So I come to you from the Tharawal First Nations lands in southwestern Sydney. These lands are part of the broader lands of the Eora Nation, and I'm acknowledging the fact that there have been Aboriginal First Nations peoples living, working and playing on these lands for many tens of thousands of years. This land was never ceded and coexists with the Commonwealth of Australia. Wherever we are, I hope that you are able to look outside and appreciate the earth, the soil around you, the sunlight that gives life to everything, the atmosphere, the air, and the water. All of these things come together to support the lifestyles that we have in today's age, which take much but give back little to the earth and the environment. Hopefully, it's initiatives like this hackathon that allow us to come together and collaborate as humans to support the ecosystem and the earth that supports us and supports all life. So thank you all for joining today. This technical workshop, we thoroughly encourage you to keep your videos on and keep your microphones muted if you're not speaking. But if you have a question, to unmute yourself and ask your questions, and also at any point in time to make comments or questions into the chat. We also acknowledge that English is not the first language for everybody on the call here. So if you would like at any point for us to repeat or clarify anything that we say, please feel free to reach out. So again, thank you for joining this technical workshop, and I now pass over to Matt Padgett from CSIRO, Australia's National Science Agency, and Caitlin Adams from Frontier-SCI, who will be walking us through this morning's workshop. In 1 hour from now, we will begin our next session, which will be the keynote session, and we'll be finishing 5 or 10 minutes just before that in order to allow you to have a comfort break. So without further ado, over to you, Matt.
There we go. Thank you very much, Roshi. Trust that's sharing the correct screen.
Yeah.
Second, I'll just try and put my chat box into play so I can see any live questions that come through here. There we go. All right, so, excuse me, voice fraction croaky, I'll take a drink in various parts. So I'm going to start with a set of slides here to talk through little of the more practical details with regard to using the EOCSI platform within this project, in this hackathon. Yesterday, I gave an introduction to the intent of the platform and what it's designed to do and achieve, and we looked at and talked about a little bit of the science opportunities that are available out of CSIRO, Geoscience Australia, and from that linking to a world of other endeavours through our various communities and networks. So this talk this morning, we go a layer deeper and we look at some of the practical aspects of working on the platform. Right, yeah, there we go, and the click through button. So there's a little overview of what we'll talk through today. Have a little review there, but we're going to talk a little bit about Earth observation data and how products are generated and created. What we have available with regard to raster and vector data, and how we request and bring our own data to the platform. And then we'll look at the platform itself. There's some excellent information in the participant handbook, so we referenced that early. Encourage you to get started there, and we'll have a look at the Jupyter Lab interface and a brief look at notebooks and so forth, and finish up this little slide presentation with some further resources and links for us. The rest of the session after that will be fairly freeform, so feel free to ask questions. We'll have a discussion. Myself or one of my colleagues, maybe Eric here, might take us through an example notebook or two, just a bit of a live demonstration, light and easy. We'll see how we go. So let's begin. When we talk about Earth observation data and products, we're talking about satellites, Earth observing satellites predominantly. And these Earth observing ones are typically measuring radiation or radio reflectances and so forth, signals reflected back from the Earth's surface or penetrating or bouncing back from the Earth's surface in some way, a measurement of the Earth as it sees it. But as satellites, they're traveling above the atmosphere. Some of the same principles would apply to airborne and drone information, but some of the pre-processing steps would differ for those ones. But predominantly, we're talking about the satellites orbiting the Earth. The main ones we look at satellite-wise are the Landsat series of satellites, European Space Agency's Copernicus set of satellites, Sentinel-1, 2, 3, 5. The MODIS series of satellites, Japan's Himawari series of satellites, and then a specialized set of satellites and sensors, and these might be high resolution, hyperspectral, and LiDAR. They're all in play and all of interest to the Earth observation community globally. These satellites are predominantly run by national space agencies and operators. There's a bunch of acronyms in the bottom left-hand box there. NASA, USGS in United States, European Space Agency, JAXA and JMA from Japan. And collectively, there's a committee on Earth observation satellites called EOCSI. And this is a representation of all the national space agencies who operate satellites or have a vested interest in some part of the workflow and chain of Earth observing satellites to users. It's through EOCSI that a lot of commonality and aggregation and best practice is promoted across the space agencies to get to us, largely to get to us at a point last few years that we have a very rich set of free and open data to use and access, and excellent set of tools to access that data. Within the operators, there are also the commercial operators. Maybe Maxar and Planet Lab are a couple of the more popular ones, but there are many smaller startup niche operators flying satellites these days as well. There's an explosion of space-based activity, as you may well be aware. Nevertheless, each of these, whoever operates them and whatever type of satellite they are, they all need to go through some level of data preparation, from the raw signal collected on the satellite through to a data product that can be used. In the EOCSI community, this is referred to analysis-ready data. It's a term we use quite regularly. It's not specific to any exact target point other than the data have been processed to a good, common, agreed level of quality and organization, such that users, us, can access and use the data with minimal effort thereafter. This is a really important feature of the the power that we have these days to be able to work with these data, the large archives of Earth observation data, efficiently and smoothly. In essence, the effort of managing and hosting and preparing the data to a near analysis ready point is done by the agencies who own the data and understand the data best. And then they provide it, ideally, in a format and through data access methods, such that we as users can grab it and use it directly. It's fantastic. Fantastic trajectory of, what should we say, technology and digital advancement in the Earth observing community over the last, probably I've seen a massive amount of change in the last 5 years. When we, as users in EOCSI and the Open Data Cube, look to connect one of these Earth observation data sources up to the data cube or into our systems, the things we're typically looking for are who are the host agency, where's the documentation for the satellite and the product, and the sensor data, what are the data access APIs available, what format are the data in, and what metadata is available to come with that. This is maybe those terms are a little bit generic for most data management activities, but we're fully across that part of the pipeline as well as we prepare these data through into our systems. So if there are, as we go through the week and forward through this process, if there are particular new satellite data sets and other data sets that you'd like to have access to, and we might be able to work with you to make them available in the platform, then guiding us towards some of those 5 criteria around the host agency, documentation, access APIs, all that sort of thing with us. They're key steps that we need to answer as we go forward in data preparation. This is a brief of the technical or scientific mechanics, if you like, of the workflow mechanics of getting to analysis ready data. Very, very simple top level 4-point sketch. In the top left-hand corner is a color corrected image of Eastern Australia taken with AVHRR satellite. It's mapped in a non-rectangular form because that's the swath projection that the satellite sees as it orbits the Earth. And when you map that swath onto a flat square, which is the image as the projection of the Earth, and as this image in PNG is created on the screen, it displays out, and you see a broadening of the swath width, if you like, in relative terms to what we might consider to be a square map, particularly towards the south latitudes and the high latitudes. The other thing to note is that it's a top of atmosphere product. It sees the clouds. This is an optical infrared sensor, the AVHRR one. So it sees the top of the clouds, and you see the land structures and ocean structures where there are gaps in the clouds. The active atmospheric correction for these data is referenced in the second picture. It's not a great quality picture. I apologise for that. I've never quite been able to find the original of this picture. But it's a nice description of what we're measuring from a remote sensing observation, be it satellite or aircraft, as in the picture. So in the case of optical and infrared, the primary energy source is the sun. The sunlight diffuses through the atmosphere, bounces off the surface of the Earth, scatters and reflects back upwards. And it's the reflected signal that's being collected by the remote sensing platform, the aeroplane or the satellite. There is a whole branch of science to look after the inversions and corrections that one has to do to change the signal received at the satellite to what this original signal might have been at the Earth's surface prior to the scattering. There are models and equations which can help with that, and supplementary data sets that, as I said, there's a world of expertise in that space. We don't walk into that space too much. We understand it's there. The third part is calibration and validation. So once we've got the signals at the surface and we're starting to assess them and produce a product of some degree, we have grids and arrays of numbers and geolocated numbers for whatever parameter we're trying to measure. And the third important step in the process is calibration and validation. And this typically requires field work, people in the field going out, measuring what the actual conditions are like, ideally at or near the overpass time of the satellite, so we can be very temporally consistent. Build up a database of field observations and then do essentially a correlation or a match against the remote sensing data. And that gives a confidence level and an opportunity to train and tune the algorithms such that the result is closer to the real field observations collected. There's really no escaping calibration and validation. It's a really important step in all of our work. So I really encourage you to consider, if we're going to build products and outputs directly off some of the satellite data, then I encourage you to consider what kind of extra additional validation data might be available to help verify and improve the confidence of the algorithm product. In our cases, that might be existing collected data sets that you know and are aware of. They might be complementary field surveys. They can be from different times and periods to some degree, depending on the type of characteristic we're trying to measure, be it vegetation or coastal change or something that might operate a little bit slower in terms of changing. It could be drones. It could be aircraft. Aircraft a little bit high in terms of they will still catch some atmosphere, but drones can be quite good at covering spatial distances. So any kind of survey data or field data that you might be aware of, and drone data is very important for some of our calibration and validation activities. And then fourth point, once we're done, we have a product and a picture, and that picture is of vegetation fractional cover. That's a product name for Queensland in Australia. Here, the colours mean green is very green, vegetated. The reds are dry and bare earth grounds, and then the blues are a bit of an intermediate mix of either dry vegetation or sparse greener vegetation with a mix of bare ground underneath them as well. In this context, the fractional cover products are a really popular one for seeing vegetation state very consistently across a wide area. So the Earth observation data is, because it's swaths and the satellite is seeing a path, it comes to us as a grid of data. And a grid of data is commonly, a term for grid of data is also raster data, and that's grids. The other type of data is vector data, which for me I consider to be points, shapes, tables of information. There are two main services available that we have within the platform for showing, interrogating, exploring, browsing data sets of both raster and vector data. For raster, we have the ODC Explorer. That's a representation of the time and space coverage and scene metadata details of all the individual items stored within the Open Data Cube database. And the second one is a GeoServer portal. GeoServers are quite common, popular, been around for quite some time. Web server for hosting shape files, vector files, tabular data, database data. It can do raster data as well. It provides web services such as a WMS and WCS, WFS if available, which is another nice way to connect to some of the data that might be in there. So between those two options, we're covering the main types of data sets. Those two cover the storage of the data sets. Once we've got the data inside our programming environment, then we have the wide range of Python geospatial libraries and packages available to us to do whatever analysis we wish. So at that point, our popular ones that we use most often at the moment are Xarray, Pandas for tabular data, Xarray for raster data, Raster.io for geospatial transformations. And then there are many other Python packages built on and underpinning these three main ones. The main point here is that once we're in the Python ecosystem, we've got a large array of analysis tools available to us. All we need to think about before that is our interface to the data and how we're going from wherever the data is available, be it Data Cube or GeoServer, into a data structure in Python that we can use. We can also bring our own data. On the left-hand table the left-hand table shows the set of data currently available in EOCSI. So Landsat 5, 7, 8, and 9 all available. Sentinel-2, some digital elevation models, MODIS ocean and land products, and some precipitation and wind products as well. We talked a little bit about Sentinel-1 yesterday. So we have a workflow for Sentinel-1 in our prototype stage, Sentinel-5P as well for atmospheric measurements, and just starting on Himawari 8 as well from the Japanese agencies. The purple boxes relate to other providers and data sources that we are aware could be of value and interest, but they're probably going to rely on custom interfaces and some sort of custom development, so we might approach them on a case-by-case basis. You can bring your own data as well, and as I say, it doesn't have to be in Data Cube, it doesn't have to be in GeoServer. Our target is to get it readable and into a Python data structure. Once you log into EOCSI, you have access to your own home directory. This is private to yourself. No other user can see your home directory. The Jupyter Lab interface and platform, standard for all Jupyter Labs, provides a file upload facility. This is a button file upload or drag and drop file from your desktop into the home directory space. Both of those will load a file over the internet through your browser. So maybe not very large files. Keep them small files, perfectly fine. Large files, consider the upload time. Within EOCSI, we have a user Scratch bucket. Scratch here refers to a shorter lifetime intermediate products. An S3 bucket means it's a storage facility within the Amazon Web Services environment. Object storage, we can work through the details of that. Relatively large size, large availability of storage capacity there. So large initiation files, intermediate files through our processing, whatever we need to use it for, it's available there. There is also a restricted access S3 bucket, and for this we can set individual user groups and permissions, and then only certain individuals can access certain paths on the bucket to access the data. So there's a few options there. Generally speaking, I think I made this point yesterday, where we prefer to work with open access data sources because the data licensing is a lot easier. But if there are specific data access restrictions or considerations, please let us know, and we'll work with you to find a suitable arrangement. Within the participant handbook, I'm sure you have read it if you've received it. Down in section 10, there's an easy user guide that our colleagues have put together. It's excellent. It's a nice little walkthrough and step through about how to sign on, once you receive a sign-on email, how to log into the system and get started in your first steps. We'll do that as a live demo, either in a few minutes or during the course of the week. We'll work through everyone into this space. In the bottom left table, there's a suite of reference URLs available to you. The main step and procedure is that you sign the participant agreement. I create an account for you. The system will send you a welcome email, and that will include a temporary password. And then we encourage you to read the documentation and see how far you can get by yourself, but let us know if you have any questions. Once we're in Jupyter Lab, this is where we do the majority of our work. Jupyter Lab allows us to test, develop, and iterate our ideas and share our ideas with other colleagues. Jupyter Lab itself is a widely used platform across a number of communities these days. So if you're new to it, then it's a good skill to learn as well. You'll be needing it in the future, quite likely, or you'll be at least a familiarity with it. It's backed up with pre-built images. An image being an operating system plus software libraries that run all the code that makes our platform work, in terms of makes each Jupyter Lab instance work. It's a Ubuntu-based image, and we pre-built a lot of the common geospatial and machine learning, Python and R libraries into these images. So most of the tools that you should need will be available, but we can also add more. The screenshot on the top right, there's two screenshots. They're just maybe blurred together a little bit. The top screenshot is what you would see with a Jupyter Lab platform and interface. When we go in, we'll explore a little bit more, but what you're seeing there is a file browser home directory on my left-hand side and my notebook open on the right-hand side. The notebook says, "Welcome to EOCSI." So it's one of our first notebooks for this hackathon. The bottom screenshot image is of Visual Studio Code. We can, included within the platform in Jupyter Lab, we can open a Visual Studio Code editor. And this lets us have nearly a full development environment for code development. For me, I tend to use Visual Studio Code in EOCSI for my own purposes these days. I use it for convenience because it has all the libraries built. I do most of my development in EOCSI, not just when I'm using EOCSI data per se. Take a little pause. To move notebooks around and small amounts of data and information, other code, notebooks and other code, I should really highlight. We use Git a lot, Git. Git is a version control system for code and systems, very popular with the developer community, if you like. Common GitHub platforms and services common Git platforms and services you might hear are GitHub, Bitbucket, and Azure DevOps. They all operate under the same Git protocol. So when we get into downloading notebooks and checking, borrowing other people's code and bits and pieces, we'd rather use Git wherever possible rather than copy and paste, I guess, because Git gives us that history and traceability as to the origin of the code and the edits we make on top of it. Another feature that in the Jupyter Lab interface that we'll be building or deploying over the next short while, maybe a couple of months, will be dashboards. So while notebooks and Visual Studio Code are really great for testing, development, and iteration of ideas, at some point we want to be able to show off our great work. And a dashboard is a way to make a simple custom web application from our code in a notebook or a script. We know what we want to do there. I say it's coming soon. We know what we want to do there. We're just working through some of the security considerations of opening up web apps and who can see them and so forth. When we build a notebook, there are this set of steps we generally always go through. We have a notebook in the top left. We choose our notebook and we select a product in an area of interest, a topical area of interest. In that screenshot, it's a small area over the city of Canto in southern Vietnam. We set up our processing, the kind of image analysis that we want to do. The number 3 label there says Dask parallel processing, which is an advanced form of parallel processing that we have access to and we will get to use quite a lot of. But we'll come back to Dask another later in the week to describe how that works. But let's say number 3, we'll interpret that as all our algorithm preparation and processing. So it might be masking of the data, filtering quality from the data, combining bands, adding supplementary and complementary data sets to build up our final product, whatever that processing is in number 3. And then we plot the results in the bottom left-hand corner. We start to look at them in our notebook. There are some very nice libraries that allow us to visually interact with cubes of data. So where we have a time-space stack of X-array data, there are some plotting libraries and tools that let us explore that through all the dimensions, which is really quite neat and powerful. I think the graphic in the bottom right-hand corner is really just a little screenshot video of me building a notebook once upon a time and working through each of the cells and triggering different events as I go through processing it all up. So coming to the end here, There are lots of resources available for learning about Jupyter Lab, learning about the Open Data Cube, and learning more about Earth observation. One of the excellent resources available is the Digital Earth Africa learning platform. And one of the real privileges and benefits of this hackathon is working with Geoscience Australia and Frontier SI, who have done the vast majority of the work in terms of building the community and building the training resources and learning materials for Digital Earth Africa. So we're very lucky to be able to build on their, or leverage and build on their expertise to deliver a similar kind of experience for Southeast Asia. On the right-hand side and in the docs, in the Easy Docs section, there's a page there with a suite of links to many of the other major Open Data Cube initiatives. And they each have their own sets of notebooks for different application types, different examples of the kind of work they do. So if you're looking for ideas, that might be a really good place to start, to have a look at that user guide page, look at each of those links and just see if anything takes your interest in terms of an application area. And with a bit of luck, someone may have already done some of the work for us that we can borrow and adapt. So that brings me to the end. Thank you. There's some contact details for some of the tech team available to you during the hackathon here. Caitlin and myself on Frontier and CSIRO sides, and we have Eric and Ronnie on the CSIRO side, and Madeline on Frontier as well. There's also within the technical team, we have representatives from Geoscience Australia joining us during each of our tech drop-ins. So they've also, as we've discussed, got a wealth of benefit in this area and can respond and talk to your questions about different application types as well. Not limited to us, but we can be an entry point. So I'll leave it there, and I might just leave the floor open for 10, maybe 15 minutes for discussion and questions. We'll take it from there.
So Matt, there's a question in the chat already from Jason that's asking, can you download some of the data from the platform?
Thank you, Caitlin. Just seeing that, yeah. You can. So back in the Jupyter Lab interface, we'll show you how to do this when we do a live demo. You can essentially right-click on a file. I'm not sure if you can see my mouse, but it's bouncing around in the file browser area of the Jupyter Lab screenshot there. And a right-click, there'll be a download file button. So again, that will download via the internet in your browser to your desktop. So maybe not do massive files. Similarly, where do we say it? When we talk about the user scratch bucket number 2 on the right-hand side there, there are tools we can use and examples we can show you about uploading, using some Linux command line tools to directly upload larger files into the easy bucket system underneath. So that can be another way, but that also works in reverse. So we can also pull stuff back out again as well. That can work. So that's 2. Number 3 option is not so much through Explorer. GeoServer has the web services available, so that will let us access and use the data sitting in there. And another service that will be hopefully coming online soon, just seeking a little bit of configuration advice from our good colleagues at Geoscience Australia, will be a DataCube OWS service and a Terria map web browser as well, which are another couple of ways to interrogate the data. For the most part, though, Jason, we'd encourage more of our work to be done in the platform. So the pattern, the anti-pattern that we would not so much encourage would be selecting large cubes of data and then trying to download them to your desktop to do your analysis on your desktop. It's not so much, shouldn't think of it, if possible, but one should think of it in the context of a data repository per se. It's more the computing platform that we're taking our work to the data rather than bring the data to us. But in terms of results, most certainly we can pull data down. Kaylin, may I have a breath and let you fill in any gaps, please?
Yeah, sure. Well, I was thinking that this afternoon's session is sort of designed to look at the gold standard. So we can save sort of, Eric, your examples for that time. And then the final session of today will be where I'll sort of go through a live demo of how to sort of start your first notebook and some sort of tips and tricks about loading this kind of raster data that we have available in the platform. And I think it's worth talking about the fact that, you know, particularly if you're new to programming at all or new to Python, this sort of information may feel overwhelming, but there is lots of really kind of common and consistent operations that you can do to put, you know, sort of build lots of little puzzle pieces and kind of plug them together. And so what I'll be covering this afternoon will be, you know, what those pieces look like and how you can start using them. And I think it's important to also talk about that during this week, we're here to support you, and the platform is here for you to try out as much or as little as you'd like to. So if you want to spend this week sort of focusing on understanding your idea, building a team, and want to leave doing additional development until, you know, the launch phase, if that's, you know, something you're really interested in doing, then we can provide you more detailed technical support to kind of get your idea off the ground. And so we have the tech drop-in sessions all week, and that's there if you want to come along. If you have, you know, you're not sure how to start on translating some of your ideas into this sort of technical space, that's why we're here. That's what we're here to help you do. So Matt, I might just pass back to you. So we've got 5 minutes left for this session, and then we'll give everyone a sort of 10-minute break before the next one. So there's a question from Bam of, are all the Southeast Asian regions accessible at the EOCSI platform already in an ARD format, or does it depend on the area? I wonder whether it's worth seeing as your screen sharing, just pulling up the Explorer and sort of having a look at what's there.
Sure.
Yeah, it's a really good question, Bam. So I think particularly in terms of the raster data set, the Explorer here is sort of a really good way to check that. So when you come to the Explorer page, as Matt's showing, it will show you the names and the description of the products. And when you click on a given product, you can actually see the tiled distribution and also the time. So you can see that this data goes back to sort of 2013, I think it was, and you can zoom in and look at specific months, and sort of the coloring of those tiles tells you a little bit about the observation density. And that can be really good to know because as a part of working with this data, Matt sort of talked about the fact that there is, you know, our satellites do pick up clouds, and so you may need to remove cloudy areas from your scenes or try and create composites to do your analysis. And that's all stuff that we can talk about and help you with, and there's plenty of existing examples. Now, Matt, do you want to speak to a little bit about the sort of ARD format and sort of what's available already as ARD and what maybe isn't?
Sure. So I think pretty confident when I say this. The list of products here, we would consider them all to be ARD. They're all analysis ready. So they've gone through an amount of preparation. They have good metadata with them, quality flags, and so forth. And they're in a regular gridded format such that we can stack and organize the data sets. To get more information on any of these products, as we drill into one, you don't actually get much. Well, you get a lot of information through this system, but there's another place we can find more documentation, which I'll come to in a moment. But as we scroll down through, we can see some of the source identifiers for where these data sets come from. We can see a little bit of how they're structured. Some of the information comes through an API as well. There's lots of little buttons to dive into an amount of metadata and characteristic information around the availability of certain scenes. One thing that's useful is, I might pull down my live notebook here where I was building things for today. We'll have a couple of data set notebooks to give more detail and structure about each of the individual data sets and where they come from and how we connect and build them in. So this one, for example, the Landsat data from USGS, there's some selected links in here that will take us to more information about each of the data products themselves, and it's this kind of level of information that we can use to confirm and be comfortable with the ARD processing that's occurred prior to us using the data, if you like.
Yeah, thanks, Matt. I think it'd be really nice to have those reference data set notebooks available for everybody. And I would really strongly encourage, as you go through the week, if you run into challenges when you sort of use our reference notebooks, or you think there's something that we could be providing better documentation for, we would really, really value that feedback. You could email Matt or me, or you could put it in the sort of, I know we have a technical channel on the Discord, or reach out to us however you feel comfortable. And it's something that we would really value. And even as you're using the platform as well, if there's things that you love or things that frustrate you, we're really open to hearing about it. So yeah, this week, it's really all about trying this, understanding how it fits into supporting your big idea, and sort of helping you develop a plan for you know, whether this is a direction that you want to go in with your idea. So I might just ask whether there's any further questions. You can always put them in the Discord at any time, and someone in the team will get back to you about it. So yeah, any further questions, feel free to turn on your mic and ask, or pop it into the chat. Okay, sounds like we might be good for now. Thank you so much, everybody, for coming along to this session. It's really great to see so many of you here and interested in the platform. This afternoon is going to be all about understanding, you know, what you can do and how to get started in sort of the real, actual hands-on component. And in particular at 4 p.m. Australian Eastern Time, so the last session of today, I will be coding live, and so you can follow along with me if you want to, or just use that time to kind of watch the steps of how we develop these notebooks. So yeah, I'll hand back to Rosh if there's any housekeeping you need to do.
Thank you. Thanks very much, Caitlin, Matt, Eric, and everyone who's online. So we're going to take a short 10-minute break now. We will come back at 12 p.m. Australian Eastern Standard Time, so Sydney time, in just under 10 minutes now. So please feel free to visit the bathroom, grab a cup of tea or water or coffee, and we will begin the keynote session in 10 minutes time. It will be exactly the same link, so please don't leave the meeting, and we'll see you very soon. Thank you.